Okay, welcome again. So, the next speaker of this morning section is a very good friend, Gilberto Bruno Pérez, and he is sending his PhD thesis under the direction of Laura Ortiz, and today he's going to talk about foliation of CP2 with a distinguished algebraic leaf.
Thanks, Social. Thanks for Laura for the opportunity and for insist in that I hear. It's really an honor for me and try to talk in English or something like that. Definitely. Okay. The talk deals with a problem in classification and foliation on CP2, on the projective complex plane of dimension 2. And we... What? Okay. So I try to talk about some general facts of foliations and some general facts about algebraic leaves. And in the middle of the talk, I try to propose a problem where these two geometric objects coexist, two cases essentially different. The first one is the critical case. Where all the solution extended, or almost all, have transversal intersection with the line at infinity, maybe with some finite points of tangency. And in the other case, the so-called non-decritical case, the line at infinity is a curve well adapted to the vector field extended. Try to draw in blue. With a finite number of points, of singular points of the extended foliation. P and Q of degree D. In the generical case, we have D plus 1 singular points at infinity. And as the line at infinity is a projective line, has a natural structure of the Riemann surface. So in this Riemann sphere, we have puncture at these ones D plus 1 points, and an advantage of have the line at infinity as solution of the extended differential equation. We can try to study the dynamics around this solution by the holonomy maps. Each loop of the fundamental group of the puncture sphere give us, by lifting the loops, the monodromy transformations. J. These transformations are all of them analytical. and has expressions like this: mu j plus pi c plus c squared and higher order terms. And the group generated by all the monodromy transformations is the so-called monodromy group at infinity. So if we want to understand the dynamics of the solutions in a neighborhood of the line at infinity, we can study the dynamics generated by the monodromy group at infinity. So now I will change the topic to algebraic curves. Algebraic curves, as was introduced on the last lecture and in the morning, are given by the zero level curve of a polynomial. Let's see. And we have, in this case, a curve on c squared again. And the analogous of the extended version for the foliation, we have here also an extension of the curve to the projective plane. This is maybe the real means of projective, of the algebraic curve. Sorry. It's called is affine algebraic curve, and in the version of the complex projective plane, we call algebraic curve. This curve, given by the zero set a polynomial, generically intersects transversally to the line at infinity at d points. So we have also, as in the foliation, a kind of local models for the curves around non-singular points that are given by the implicit function theorem. The implicit function theorem says us that if at one point of the curve you have a non-vanishing tangent vector, you can parametrize the curve in a neighborhood the partial p is not zero, then exists a parametrization of the W variable in terms of z. Is equals to z equals 0. So the interest points in a algebraic curve maybe are the singular points, points where the implicit function theorem fails. So if we have a singular point, that is, the implicit function theorem fails, we also can obtain a parametrization, a good parametrization that is given by the Newton theorem. That gives us, I try to put an example. Before that, the statement of the Newton implicit theorem, we can consider the curve given by the polynomial W, for favorite example, C3. This curve in the real plot looks like something like that. So we have here at the origin a singular point where the implicit function theorem fails, and we have a parametrization of the curve given by the t squared and t to the cube. So the Newton implicit theorem says us that in the singular case, we always can obtain a parametrization like this. So I try to draw the geometric version of the Newton implicit theorem that says something like that. We have here the curve at the neighborhood of the singular point, and the curve looks like, try to draw. We have here the complex parameter t. We have here the parametrization, and have here the projection of the curve on the first coordinate. And here T to n, where n is the multiplicity of the curve at the point. That is a kind of measure that how much fails the regularity of the curve at each point. So we have something like that. If we and in the projection, the singularity is in this draw is unfold on n preimage, and the preset parametrization is given by something like Tn, and in the second coordinate we have always an analytic function of t. So, okay. one more thing. The parameterization, the Puiseux parameterization is unique. What marker? Up to maybe an analytic change of parameters, whatever that means. Okay. So we try to put the two objects in a common place. So we have a foliation of the projective complex plane. And we have to understand what is the analytic class of this foliation. What means that? We will say that two foliations are analytically equivalent if there exists a projective transformation that sends the solution curves of the first one on the solution curves on the second one. The solution to P, let me put as the leaf of the first foliation through P into the leaf of the second foliation through HP. So where two places are linked? If we have a distinguished leaf of the first foliation, in this case, an algebraic leaf, a leaf given by the zero set of a polynomial, we have that as this transformation is projective, we obtain on the second foliation an curve of the same type. I mean, if we have C algebraic, the second one, the image of C under H is also algebraic. Then we have the next fact. The foliations are analytically equivalent implies that P, and let me call this D, C and D are also analytically equivalent. And moreover, if the curves has singular points, we need that also they are locally analytically equivalent. So what says us these implications that the locally analytical equivalence between the leaves is a necessary condition for the analytical equivalence between the foliations. So let me put here analytical equivalence, local equivalence. Between foliage, between curves. A necessary condition for the analytic equivalence FB and BT. So with this fact as motivation, we have the following problem. That is, determine the influence of the local analytic invariance for curves on the classification, the analytic classification of foliations. Projective equivalent foliation. Yeah. Yeah, projective, but yeah, projective. I find yes, because we will work on this case. So if we have the line at infinity as a solution, we want to keep as the same solution. So the projective transformation that fixes the line at infinity are all of them affine. So let me try to give you a briefly context on the some interesting invariants for curves. For curves, we have an analogous definition by the equivalence. We say that two local curves are equivalent if there exists a transformation that sends the first one on the second one. And what is the meaning of equivalence here? I try to say it as Laura said in their courses. But depends on what glasses you put for the equivalence. If you want to classify the curves under the topological glasses, you have to require to H be an homeomorphism, a continuous transformation with inverse of the same type. If you want to classify with the analytic glasses, you have to require to H be analytic with inverse of the same type. So in the case of local analytic curves that are called branches. The topological classification is well known. It's called the singularity of the curves. Singular classes are well known, and there are a lot of informations, equivalence between them that determines the equisingular class of a curve. I will put here the characteristic class of the curve, that is a data involved in the terms of the Puiseux parametrization of the curve, that is the multiplicity, and here appears another integers on the Puiseux parametrization of the curve. So we have, this is the characteristic of the curve. We have that two curves, two local branches are topologically equivalent. This is in the sense of topological. If and only if the characteristics are the same. So, as a starter point, the topological classification on the 60s, that is analyze now the analytic classes. So by the topological equivalence, we have in the world of branches a first partition given by the equisingularity class. All of these parts of the partition are labeled by the characteristic class. So Zariski starts here. He fixes the characteristic class and asks about the classification on a fixed characteristic class. So Zariski did an important remark that relates the analytic classification of the curves through their Puiseux parameterization. Zariski notes the following fact. If you have two local branches that are analytically equivalent, by the Puiseux theorem, you have, for the first one, a Puiseux parametrization, and you have, for the second one, also a Puiseux parametrization. And he notes that the composition H phi followed by H is again a parametrization of the curve D. So by the uniqueness of the Puiseux parametrization, we have here a local change of parameters. So the analytic equivalence between the branches give us a kind of equivalence between their Puiseux parametrization. So he introduced the notion of the A equivalence between the parametrization of the curves. So here is that phi followed by h is equal to tau, the local change of parameter, and c, the A equivalence between c and phi. And moreover, he proved that two analytic local branches are analytically equivalent if and only if the respective Puiseux parametrization are A equivalent. So Zariski change of the place to study the analytic classification on curves to a problem in classification of parametrizations. So what is the purpose of Zariski? Zariski tried to find in a fixed characteristic class a representant with the most simple Puiseux parametrization. So he gave two criterions. Elimination. He gave a conditions on the terms of the Puiseux parametrization. When you can do a kind of cleaning, I don't know, do a kind of cleaning on the parametrization. And he proved also that the first term that not satisfies the elimination criterions is an invariant the analytic equivalence for branches. So we have a fierce invariant in the analytic classification or between branches, and this invariant that we will denote by lambda is not complete. That means that you can have two branches with the same Zariski invariant, but they not necessarily are equivalent. If they are equivalent, they have the same Zariski invariant, but the inverse is not true. So after that, ¿Sabes cuánto tiempo tengo? In the 90s, Rosa Pereira analyzed the problem of the analytic classification with the techniques of Zariski in this X singular class, where n and m are integers, n less than m, and greatest common divisor of n and m is 1. And she proved that if we have a curve, a singular curve with invariant lambda, Zariski's invariant lambda, in a suitable coordinates, we have C defined by the equation W n C m plus alpha q plus finite number of terms. She proved that this pair codify the existence of lambda in the parameterization, in the Poiseuille parameterization of the curve, and she characterized all the pairs that produce terms on the Poiseuille parameterization that not satisfies the elimination criteria. So at the end, this result from the work of Rosa come back to the algebraic curves. So I try to convince you that if we obtain some positive results about this problem that is a lot of general, we can start by solutions algebraic of foliation of CP2. So I try to, by the time, I try to present for you some general facts of foliations having an polynomial vector field as at the beginning of degree D that are non-decritical and tangent to a fixed algebraically. So in this case, the algebraic curve C is a curve well adapted to the vector field. So in consequence, it's a solution of the differential equation. So in this case, we try to analyze the set of vector fields tangent to algebraic curve C. So in this case, if we have two vector fields that are tangent to C, And if we consider the sum of the two vector fields, the vector field resultant is again tangent to the C, the curve C. And also, if we have a vector field tangent to C, and if we rescale by complex numbers the vector field, again, we obtain a tangent vector field to the curve. So all this has a vector space structure. So there are natural questions as, for example, what is the dimension of this space over C? And another fact that is convenient for the analytical equivalence is, as in the Adolfo question, we want to preserve the important or the distinguished object in my study, so we will consider transformations, projective transformation that act as a set fixes to C. We will talk about projective symmetries of C. So we will do the analytic classification in first instance by only projective symmetries of the C, curve C. Let me final part of the talk fixes C as the curve plus C4 equals 0. This curve is come from the Pérez theorem, and for this curve we have a singular point at the origin of C2, and this singularity has the Zariski invariant thing, and is more or less easy to prove that the symmetry of C are given by rotations on the axis further just in this case is 7. So this curve at infinity, we have something like 0 and cuts the line at infinity in the 3 cubic roots of alpha. And if we consider the space of foliations given by vector fields of degree 4 tangent to C, we have generically 5 singular points at infinity, That means that there exists another singular point that is not come from the curve C. We can prove that the complex dimension of these spaces is exactly 2. There are 2 vector fields that generate all the foliations in this space tangent to C. And as a first result, we can prove that there exists alpha is fixed, yeah. And alpha is always a non-zero complex number. Locally, we can do alpha equal to 1, but globally, no. So given a point, the line at infinity that is not, see, there exists a unique foliation here, having P as singular point. So I think that is a first positive progress in this problem, because on one hand, the symmetries of the curve are determined in some sense by the local invariant of the curve, the unique singularity on C2, and the information that not comes from the curve, that is the singularity of the foliation on the line at infinity, determines completely the foliation. So if we know all the elements in this space that are determined by the curve and by its singular point, we can try to find the analytic classes. So if we have two foliation, it looks only around the line at infinity, because the information that determines the foliation is here. So the origin and the three cubic roots of alpha, and the extra point. To alpha 3, and let me call P and P. The question is, when these two foliations are analytically equivalent. So we can prove that as the symmetries of the curve are given by rotation in two axes, it's not difficult to prove that as restriction on the line at infinity, we have rotation, classical rotation, and Möbius transformation that is a rotation of order 3. So if the foliation FP given by the vector field B and the foliation induced by the vector field B tilde, if they are analytically equivalent, then B tilde is let me six roots of the unity. So if they are analytically equivalent, then we can obtain P tilde by the original point P by a rotation of order 3. And we can prove that not only is a necessary condition, also is a sufficient condition. And that's all. Thanks.
Questions or comments?
How did you pass from the projective line over there to the Riemann surface?
The line at infinity is a complex projective line that has naturally a Riemann sphere.
Okay. And when you can this theory be generalized to varieties, algebraic varieties? Because we can think that algebraic curves are some type of algebraic varieties. So can we extend this to an abstract variety? Do you know any of that?
I think that maybe yes, but the problem on CP2 is sufficient difficult to go to another algebraic variety. Yeah. Well, I don't know.
Thank you.
Repeat, please, the Zariski elimination criterion.
The Zariski, I didn't mention about them, but comes from relations on the terms of the preset parametrization. He gave two criterions. Maybe Ociel. We will give us more details after his talk. I tried. The idea is analyze analytic curves here, and the elimination criterion depends on the intersection multiplicity with the original curve that are maybe given by so I don't know what to say. He realized as a kind of
the idea is use that relation. You need to find a biolomorphism and change of parameter to try to eliminate some terms in this parameterization, to find a polynomial parameterization. So the idea is the singularity class is classified by the semigroup or the multiplicity intersection of the curves. So Zariski gives some criteria in terms of this semigroup. So he gives the recipe that is you take a biolomorphism that is that has the identity as the linear pair plus a polynomial, and that polynomial is related to the intersection multiplicity of the curves.
One can imagine this process as in the Poincaré's linearization theorem.
More questions?
Can you comment on your result with the assertion of Gomez-Mon and Olivares? because you are provided an algebraic leaf and study the singularity at infinite, no?
Yeah.
And produce a parameter P, no? That
Okay,
is a
yeah.
singularity at infinite. Then
In this case, there are really the important object is that the complex algebraic leaf. So really, we can obtain here a description, a total description of all foliation here. So in this case, this space has dimension 2 over C, but when we are interested only in the foliation, you can re-escalate the vector field. So, but out from that, I don't know how to match.
Comment?
One, just one. In the finite, I don't know, but on the line at infinity, only one is not in the curve. Yeah. And if you take greater degree on the foliation, you will obtain a lot of points that are not in the cube. But in the fin part, yeah. But as the information at infinity determines, I didn't do the compute on the fin part.
More questions?
Okay, sorry for my English, but can you explain me
After
why
my English.
No, can you explain me why the point that it's not in the curve is a singular point, or how it appears there?
As a general fact, when you have a polynomial vector field of degree d, you have generically exactly one more singular points of the line at infinity. If we looks the points on the line at infinity of the curve, their points, these points are the origin of the local chart and the three roots of alpha, and this is the fact. You have the cross of two invariant curves in the foliation, and the crossing places between two invariant curves always are singular. So you have the line at infinity as a solution, and also we have the algebraic curve C as a solution. So these 4 points always in this history are singular points. Those are points of the intersection of two invariant curves. And the other one is information that is comes from the foliation without the algebraic curve.
Okay, more questions? Okay, if not, thanks, Gil.